Welcome to the Deep Dive, where we plunge into complex topics, sift through a stack of sources, and bring you the essential insights you need to be truly well-informed. Today, we're tackling a challenge that resonates with, well, almost anyone building software. How do you design systems that not only scale but also adapt and remain maintainable, not just for the next quarter, but for years, even decades? The traditional wisdom, as one of our sources powerfully puts it, often leads us down a path where software is easy to write but hard to change. And if you've ever found yourself untangling a mess of interconnected code, you know exactly what that feels like. But what if there was a different approach? What if you could fundamentally shift your perspective on designing and building robust systems? Moving from, say, a tangled web to a clear, evolving narrative of what your system actually does. That's precisely what we're going to explore today. We're going to take a deep dive into how architectural patterns like event sourcing and microservices, specifically leveraging the formidable power of vanilla PostgreSQL. Yes, good old Postgres can truly revolutionize your software architecture.
Yeah, and our mission for this deep dive is, I think, incredibly clear. We're going to unpack the core concepts of event sourcing, showing you exactly how a powerful, battle-tested relational database like PostgreSQL can function as your robust single source of truth, your event store.
Okay.
We'll then explore what this fundamental shift means for managing your data effectively, achieving true scalability in ways you might not have imagined, and even simplifying the often dreaded task of debugging your applications.
Right.
And this isn't just about high-level theory. We're going to delve into practical, real-world examples that you can apply immediately, especially if you're looking to implement these principles, regardless of your specific frameworks or programming languages.
And to guide us through this intricate landscape, we've pulled insights from some truly fantastic material. We've distilled actionable knowledge from a leading book on practical microservices and from the in-depth documentation of a popular event store framework. We've gathered all the nuggets just for you, so you don't have to. Let's get started. So let's begin where many software projects find themselves. The common monolith dilemma. If you've been in software development for any length of time, especially with traditional CR, create, read, update, delete applications, it's incredibly natural to model all your data as rows in a relational database. This approach often leads to what's known as a canonical data model, essentially a single, all-encompassing shared representation of an entity, like a user or a product. Let's imagine a typical videos table in a streaming platform. On the surface, it seems perfectly sensible. You'd probably have columns like id, owner-id, name, description, view count, and transcoding status. Okay, now stop for a moment and really think about this table. The owner-id is clearly about who owns the video and their permissions, something related to user authorization.
Right. Authorization logic.
Exactly. The name and description are for displaying information to a user in a video player.
Presentation layer stuff and
transcoding status.
Yeah.
That's definitely about a background job, maybe converting video formats. Completely different concern. You've got distinct concerns, almost entirely unrelated business processes, all crammed into one table. Can you truly imagine a single atomic operation within your application that simultaneously requires all 6 of those pieces of data?
It's pretty rare, isn't it?
It's rare. This seemingly simple videos table quickly highlights the deep inherent coupling that gets baked into such a shared data model.
And that right there is the crucial insight. That canonical data model is the monolith. Regardless of how you deploy your code, what programming language you're using, or what framework you've chosen.
So it's not about the deployment artifact.
Not fundamentally, no. The fundamental problem isn't about having all your code in one giant application bundle. It's about having a single, shared, and often implicitly interdependent data model. Changes to one part of this shared model can, and inevitably will, unexpectedly break other, seemingly unrelated parts of the system.
Oh, yeah.
Imagine trying to rename a column in that videos table, or changing the data type of view count.
Your weekend just vanished.
Exactly. Suddenly your weekend plans evaporate because you have to meticulously check and update every single piece of code across your entire application that might touch that table, just to be sure you haven't introduced a hidden bug. And this stands in stark contrast to a common misperception that pervades the industry. Many development teams, when they hit a productivity wall with their monolith, are often told, just extract microservices.
Right, the silver bullet.
The common but flawed approach is to simply take existing, tightly coupled functionality and separate it onto different servers.
Wow.
But if the underlying data model remains shared or implicitly linked, all you've done is create a distributed monolith.
Okay, so you've just spread the problem around.
Precisely. And what's truly fascinating here, and often overlooked, is that you've paid a significant operational price for this. You now have 2, 10, or even 50 servers, each perhaps with its own database, requiring more complex deployment pipelines, more monitoring, and likely more teams to manage them.
More complexity.
Right. But you've received absolutely no value in terms of true modularity or reduced coupling if the underlying shared data model hasn't changed. What used to be a simple, fast join operation within a single database now has to be painfully re-implemented in application code, often through slow and brittle HTTP calls between services.
Ugh. Network calls instead of a join.
Exactly. Your operational costs skyrocket dramatically for no real gain in autonomy or flexibility. You've introduced network latency and potential failure points where none existed before.
You've hit on something vital there. You've essentially gained nothing but headaches and added complexity. So the fundamental shift we're advocating for, the core idea behind today's deep dive is this. Instead of modeling data as a mutable current state in rows that are constantly updated and overridden, we'll model every state transition as an immutable historical event.
A fact.
A fact. And instead of different parts of the system communicating implicitly by simply reading from or writing to a shared database, they will communicate through explicit message contracts.
Explicit contracts.
These contracts define exactly what information is shared and how it will be exchanged, making dependencies crystal clear. This changes everything. Okay, that sets the stage. So how do we fundamentally shift away from that monolithic data model? It all starts with a concept called event sourcing. For listeners who might be new to this, how would you break down its core idea?
Right. At its very heart, event sourcing is about capturing all changes to an application's state as a sequence of immutable events. These events are then stored chronologically in an event store, forming a complete, unalterable log of everything that has ever happened in your system.
A log of everything.
Exactly. This log is your source of truth. The current state of any entity in your system isn't stored directly in a single row that gets updated. Instead, it's derived by replaying these events, either from the very beginning or maybe from a recent snapshot. We'll get to that.
Okay.
Think of it like a bank ledger. Every single deposit, withdrawal, and fee isn't just an update to a current balance field. Instead, each is an immutable sequential entry in a ledger.
Right, you see every transaction.
Precisely. To find the current balance, you simply sum up all the entries. If you want to know the balance at any point in history, you just sum the entries up to that specific date. It's a perfect, auditable history. And this approach offers truly profound advantages for your systems, especially when it comes to long-term maintainability and evolution. First, there's auditability. Because every single state change is recorded as an immutable event, you gain an exact, verifiable history of everything that has transpired.
You can see exactly what happened when.
Exactly. You can trace back the precise sequence of actions that led to any state in your system. For example, a user didn't just register and then appear in a user's table. With event sourcing, you'd see a user-registered event at a specific time with specific details, possibly followed by a registration email sent event.
Much more granular.
Absolutely. This provides unparalleled transparency and accountability, invaluable for debugging, compliance, or even just understanding user behavior over time. Then we have replayability. Because events are immutable, ordered, and represent facts, you can replay them at any time to reconstruct an entity's state, or even build new views of your data.
So you can rebuild state.
Yes, and this is incredibly powerful for several reasons. Imagine your business needs change, and you realize you need a new report that requires data you weren't explicitly tracking in your old current state tables.
Okay.
With event sourcing, you can simply rerun all your historical events through a new projection, generating this new view of data without having to migrate or transform your core historical facts.
No painful data migrations.
Well, fewer painful ones, maybe. It's also a game changer for schema migrations, allowing you to evolve your data models without destructive transformations to your primary storage. This leads us directly to tremendous flexibility in querying. Since your events are the ultimate source of truth, you're free to materialize various read models or projections.
Projections, okay.
That are specifically tailored to different query needs. These read models are entirely separate from your write model, the event store itself.
Right, separating read and write concerns. CQRS territory.
Exactly. This means you can optimize them for specific UI screens, for analytical dashboards, or for complex reporting requirements, all without impacting how new events are captured and written. You can essentially slice and dice the same raw foundational event data into whatever shape best serves a particular query, offering incredible agility to meet evolving business needs. And finally, there's robustness. The immutable, append-only nature of event storage fundamentally ensures the integrity of your historical data.
Once written, never changed.
Correct. Once an event is recorded, it's a fact. It cannot be changed or deleted. This provides an unparalleled level of data integrity and reliability, simplifying backups and recovery processes as your core data is always a verifiable log.
That's a fantastic breakdown. So we've got this stream of immutable facts, this perfect historical ledger. Let's dig into the specific concepts within event sourcing that truly bring this to life and allow us to build systems around it. As you just highlighted, events are the source of truth. They are a fact that has happened in the past, always immutable, and stored sequentially. It's like a never-ending log.
The system's memory.
Next, we have aggregates and event streams. An aggregate is a core concept here. What is that exactly?
Think of it as a consistency boundary within your domain. It's a logical cluster of domain objects that are treated as a single unit for purposes of data integrity and transactions.
Like a user profile or an order.
Exactly. Any changes to an aggregate, like a user updating their profile, result in new events being appended to its dedicated event stream. This stream is simply the ordered sequence of events for that specific aggregate, usually identified by a unique ID, like identity UUID for a user's identity.
So one stream per user, for example.
Typically, yes. Events within a stream are stored in the exact order they occurred, preserving the causal history. Our sources really emphasize that streams group messages logically, typically by an entity or a specific business process. Beyond individual aggregate streams, we also encounter category streams, like identity, which would contain every event from all individual identity UUID streams, useful for certain kinds of queries or projections.
Like listening to all user events.
Precisely. And then there are command streams like identity.command-UID, which store the requests or intents that are sent to an aggregate, potentially leading to new events.
So commands are the requests and events are the results.
That's a good way to think about it, yeah. These commands and the events they generate then feed into what we call projections. Projections are essentially the read models derived from your event streams. They're different views or interpretations of the raw event data, tailored specifically for querying.
Right, the outputs for the UI or reports?
Exactly. They get updated by listening to event streams and reacting to new events as they arrive. For instance, if you need a quick list of all active users to display on a dashboard, a projection would consume user-registered events and update a denormalized user view table that's perfectly optimized for that specific query.
Okay, making reads fast.
And finally, a key optimization for performance: snapshots. These are optional but incredibly useful when an event stream grows very long.
Because replaying thousands of events could get slow.
It could, yeah. A snapshot is a full state capture of an aggregate at a specific point in time, essentially its state at a particular version number. The brilliance here is that instead of replaying hundreds or thousands of events from the very beginning to rebuild an aggregate's current state.
You start from the snapshot.
Exactly. You simply start from a recent snapshot and only replay the relatively few events that occurred after that snapshot. This brings us to a really important question. When should you actually use snapshots?
Good question. Do you always need them?
No, definitely not. The strong recommendation, which aligns perfectly with the keep it simple, stupid KISS principle, is to use them only when you actually encounter clear, observable performance issues that necessitate them.
Don't pre-optimize.
Exactly. Start simple, measure, and then add snapshots if the need arises. Keep it simple first.
So this all sounds incredibly powerful, but for many, the term event store immediately conjures images of complex, specialized databases or distributed systems that are intimidating to set up and manage. What's the secret to leveraging something as battle-tested, reliable, and familiar as vanilla PostgreSQL to do this heavy lifting? Can Postgres really do this?
That's a fantastic question, and it's where the practicality of this approach really shines. The core concept here is building what we call a message store right on top of PostgreSQL. When you strip away the fancy names and complex infrastructures, a message store fundamentally needs to provide two things. First, it must reliably persist append-only streams of immutable messages, meaning once a message is written, it's there forever in order.
Append-only, got it.
Second, it needs to provide robust, optimistic concurrency control on those streams, ensuring that multiple attempts to update the same piece of data don't stomp on each other.
Right, avoiding race conditions.
And the beauty is, PostgreSQL, with its rock-solid transactional capabilities and indexing features, is perfectly capable of doing both and doing them incredibly well. In practice, a robust message DB built on Postgres often boils down to something surprisingly simple. Typically, a single messages table with a few well-placed indexes.
Just one table.
Often, yes, for the core message storage, and a set of carefully crafted user-defined functions, stored procedures, for all your interactions. You're not directly querying or inserting into this table from your application code for writes. Instead, your application makes calls to these Postgres functions, which handle the underlying logic for append-only storage and concurrency.
So when we talk about this messages table, how exactly is it structured? Is it a traditional relational table that developers would recognize, or does it need to be quite different to handle these append-only immutable events efficiently? My gut says it's optimized for writing rather than reading.
Your gut is absolutely right. You won't find traditional third normal form tables here, optimized for reading. These tables are purpose-built for writing specifically, for appending new events quickly and reliably. If we look at a typical messages table structure, you'd find a few key columns, an ID, a UEID for a unique message identifier.
Okay, standard primary key.
A stream name, like viewing videoid to group all messages related to a specific video viewing session, or a userid for all user-related events.
That's the stream identifier.
A type which indicates what happened, for example, video viewed or user registered. Data, which is typically a JSON-B column holding the actual event payload.
JSON-B.
Very flexible, yes. And metadata, another JSON-B column for cross-cutting concerns, like a trace ID for distributed tracing, or the user ID of the person who initiated the action. It also includes position, the order within its stream, and global position, its order within the entire store, and a timestamp.
So position within the stream and globally.
Correct. The distinction between data and metadata is crucial. Data is your domain-specific business payload, and metadata handles the plumbing for distributed systems, ensuring you can follow a chain of events. When it comes to writing messages, your application interacts exclusively with a PostgreSQL user-defined function. Let's call it writeMessage.
A stored procedure, basically.
Essentially, yes. This function is powerful because it encapsulates the logic for ensuring integrity. It might take parameters like ID, stream name, type, data, metadata, and crucially, expected version.
Expected version for concurrency.
Exactly, we'll come back to that. The type parameter is key. For events, it tells us what did happen, always in the past tense, like video viewed. For commands, it's imperative, telling us what we want to happen, like register user.
Okay, past tense versus imperative.
And the metadata is where you'd include important tracking information, like that trace ID we mentioned, which ties all messages resulting from the same user input together across your distributed system. So for instance, when a user watches a video, your application simply calls this writeMessage function, passing a video viewed event payload to a viewing X stream, where X is the video ID. Postgres handles the atomic append, ensuring data consistency.
That's a great practical example, and it really clarifies how simple the core interaction can be. But this often leads to a common question from developers. Can't Kafka do all of this? I hear about event streams and immediately think Kafka. What's the distinction here?
It's an understandable and very common question, but it's crucial to distinguish their primary purposes. Kafka is indeed a powerful, high-throughput message broker, exceptionally good at handling vast numbers of events and moving them around efficiently for real-time processing and stream analytics. It's a fantastic transport layer.
Right, for moving messages.
Exactly. However, a message DB, or an event store, built on PostgreSQL, is fundamentally about storing those messages as the immutable source of truth, providing transactional integrity for writes, and offering a queryable history.
So, storage versus transport.
Largely, yes. They serve different purposes within a larger system. You might even use both Kafka to transport events to various consumers, one of which might be persisting them into a Postgres-based event store. What's truly fascinating here, and a point Greg Young, a well-known figure in the event sourcing community, often emphasizes, is that what is a queue but a degenerate form of a stream?
Interesting.
By using an event store, you're building a more powerful, persistent form of a stream that gives you a complete, immutable history of facts that have happened in your system, something a transient queue or a pure message broker might not offer. You get auditability and replayability baked in.
Now that we understand how PostgreSQL can serve as our robust vanilla message store, the next big question is, how do we build independent, scalable pieces of our system? what we call components, that can actually interact with this store and truly achieve the promise of microservices, not just the distributed monolith.
Right. If we connect this to the bigger picture of escaping the distributed monolith, the answer lies in a powerful, strict, but ultimately liberating rule. Stream boundaries are component boundaries.
Stream boundaries are component boundaries. Okay, what does that mean in practice?
It means a single component is authorized to write to streams within a specific category. For instance, only your identity component would be allowed to write events to identity streams, like identity userid stream. No other component touches those for writing.
Strict ownership.
Very strict. This rigorous separation is fundamental. It prevents the insidious coupling we discussed earlier, where in a traditional monolith, anyone can add columns or update rows in a shared table, leading to unexpected breakage across the system.
Right, that shared table problem again.
Exactly. This discipline is precisely why you can truly extract microservices and achieve true autonomy, rather than just distributing a monolith. It ensures each component is sovereign over its own data and its own slice of the domain, drastically reducing intercomponent dependencies and enabling independent development and deployment. Let's walk through a practical example like user registration. Instead of thinking about a user-created event, which is very CRU-centric and doesn't quite capture the business intent.
Yeah, created sounds like a database operation.
Right. We design a register user command that, if successful, leads to a user-registered event. Why user-registered? Because it's deeply domain-centric. Most people don't think in terms of database operations. They think about signing up.
Makes sense.
Yeah.
It reflects the business process.
Precisely. So, when a user submits a registration request, a register user command is sent. Your identity component processes this command. If everything checks out, say the email isn't already taken, the component then writes a user-registered event to an identity usered stream in your PostgreSQL message store. This event is an immutable fact. This user has registered. This clear flow of command to event makes debugging and understanding the system's behavior much simpler.
So once these components write their events to the message store, what do they do with them? That's where projections come in, and it's important for our listeners to understand that the term projection has a couple of key distinct meanings in this architecture. This is a source of common confusion, so let's really unpack it.
Good idea. It trips people up.
The first meaning is what we call component-level projections, or live aggregation. This is primarily used by the writing components themselves to get the current state of an entity by replaying its own stream of events on demand.
Right.
Correct. On demand, in memory, usually. The process for this is quite straightforward. When a component needs to operate on an aggregate, it reads all the events for that specific aggregate stream from the message store. It then orders them chronologically, constructs an empty object for the entity, and then applies each event sequentially to that object, effectively rebuilding the current state of the aggregate in memory.
Yeah, just for that specific aggregate instance it needs to work with.
For instance, before the identity component can process a new register user command for a specific email, it might need to know if that user is registered already. It would do this by projecting the identity userid stream for that user ID.
Exactly. It loads the history, replays it, gets the current state, then decides if the command is valid. And it's absolutely critical to understand that these live projections, used for reconstructing the aggregate state, absolutely never trigger side effects.
No side effects. Why is that so important?
They are pure functions. They always and only return new copies of entities having applied a new event to them. This ensures that when you replay events, perhaps for debugging or building new projections later, you can confidently do so without re-executing external actions like sending emails, charging credit cards, or making API calls.
So replay doesn't accidentally resend 100 emails.
Precisely. They are solely about state reconstruction for internal decision-making.
That makes perfect sense. Okay, so that's the first type of projection. What's the second?
The second meaning applies to what we call aggregators or asynchronous projections. These are separate background processes that consume events from the message store and create, then persist, read-side views, what we often call view data, specifically tailored for various query needs.
Okay, so these do persist data, unlike the live ones.
Correct. They build and maintain the tables or documents that your UIs or APIs will query directly. These views are eventually consistent, meaning they will catch up to the latest state of the events, but there might be a slight acceptable delay.
Eventually consistent. Important term.
Very. The process for an aggregator is to continuously listen to a stream of events from the message store and then update its corresponding view data. This view data could reside in another PostgreSQL table, a document in a NoSQL database like MongoDB, or even a search index like Elasticsearch, depending on the query requirements.
So you choose the best storage for the specific read need.
Exactly. You optimize for the query.
A great practical example here is our homepage aggregator. Imagine your homepage needs to display a global count of videos watched across your entire platform.
Okay.
Rather than trying to query the main event store for every single page load, which would be incredibly inefficient.
Yeah, you wouldn't want to do that.
This homepage aggregator listens specifically for video viewed events from all relevant streams. As it consumes these events, it updates a simple pages table that might just have columns like page name, it's all homepage, and a page data JSON-B blob that contains our videos watched count.
Just incrementing a counter in a JSON blob.
Exactly. This allows for a single, highly optimized query for the homepage, delivering that count almost instantly. This is where message-based architectures become particularly interesting. You can slice and dice the same immutable event data, your single source of truth, into literally whatever shape is required for your specific read needs, without impacting your core write model.
And we can even simplify this for certain types of metrics or analytical needs. A flat table projection, for instance, can be used to derive metrics against a simple SQL table directly from events. This optimizes for standard SQL queries against a flattened structure.
Like for dashboards or reporting.
Perfect for that. Understanding trends like average file sizes over time or tracking overall system traffic patterns. Simple SQL against a simple table built from events. One final crucial point on projections: they are ultimately code.
Right. The logic lives in code.
When your code defining the projection changes, for example, if you add a new property you want to derive, or if the logic for calculating a metric evolves, you will need to rebuild that projection.
Rebuild, meaning reprocess all the events.
Often, yes. This means reapplying all the original events from the message store to the new projection code to maintain a correct and up-to-date state. This rebuild process ensures your read models accurately reflect the new business logic without needing complex data migrations on the production system. You just replay history through the new code.
Now, perhaps the most critical concept in this entire architecture, and one that is foundational to building resilient distributed systems, is idempotence. It's a word often thrown around, but truly grasping its necessity is vital. Can you unpack that for us?
Absolutely. And I can't stress this enough. This concept is as important to microservices as oxygen is to you, dear listener.
Okay, that's a strong statement.
It needs to be. Let me be blunt. Messaging systems will fail, or more accurately, they will deliver messages more than once. It is physically impossible to guarantee exactly once delivery in a complex distributed system with network failures, retries, and restarts.
So exactly once is a myth.
In practice, yes, for end-to-end delivery guarantees, you will see the same message more than once. Therefore, you, as the consumer and handler of messages in a message-based architecture, must account for the fact that you'll eventually process the same message multiple times. You must write idempotent message handlers, as we often say. Go idempotent or go home.
Okay, message received. So how do we practically achieve this? What are the strategies for writing idempotent handlers?
For insert operations in PostgreSQL, a common and incredibly effective strategy is to use the on-conflict do-nothing clause.
Postgres' upsert capabilities.
Exactly. For example, when an aggregator processes a user-registered event and needs to insert a user's basic credentials into a user credentials table, perhaps for login purposes, your SQL insert statement would include on-conflict userid do-nothing. If a record with that primary key, the userid, already exists because the event was processed once before, PostgreSQL simply does nothing.
The second time it just ignores it.
Precisely. The operation is effectively a no-op on subsequent attempts, preventing duplicate rows and maintaining data integrity.
Okay, that handles inserts. What about updates? You can't just ignore those.
Right. For UPdate operations, you need a slightly different approach. You can use something like a last process global position or last event version field on your read model.
Track the last processed event.
Exactly. When an update needs to occur based on an incoming event, your update query includes a where clause that ensures the update only applies if the incoming event's global position or version is greater than the last process global position that you've already recorded on that specific read model row.
So you only apply newer events.
Correct. For instance, when incrementing the videos watched count on our homepage aggregator, the update query would be structured to say, update pages, set page data, videos watched are int +1, last event global position, new global position where, page name hold position, and last event global position.
Checking that last event global position.
Right. If the same video viewed event is processed again, that where condition won't be met, and the update won't run a second time, ensuring the count remains accurate. It's also worth noting that it's important to understand the trade-offs involved. Sometimes duplicate work in an external system is acceptable or even preferred.
Like sending an email twice.
Potentially, yes, if the consequence of not doing the work is worse. For example, if you're sending an email based on an event, sending it twice might be less problematic than not sending it at all, especially for a crucial notification. Your idempotent check would still ensure that the email sent event is only recorded once in your events store, but the actual external email sending action might reattempt.
Okay, so the record of sending is idempotent, even if the action happens twice.
Exactly. Similarly, retranscoding a video if a video published event is reprocessed might be perfectly fine if transcoding is a cheap CPU-bound operation, and the business considers failing to transcode a video a much worse outcome than doing it twice.
So it's a business decision, too.
It always comes back to that. These are the kinds of nuanced discussions you'll have with your business stakeholders to determine the acceptable level of idempotence and potential duplicate side effects.
That deep dive into idempotence was critical. Now let's connect this to CQRS command query responsibility segregation. This pattern explicitly separates the write model from the read model. How does this separation help us navigate the trickier scenarios in distributed systems, especially when dealing with unique constraints and managing concurrency?
Yeah, CQRS is truly fundamental to making this architecture scalable and maintainable. It explicitly separates the command, or write, side, which is laser-focused on capturing state changes as immutable events.
The event store.
Right. From the query or read side, which is focused on delivering highly optimized, denormalized views of data for specific query needs.
The projections.
Exactly. This separation allows you to optimize each side independently. Your write model is optimized for transactional integrity and capturing facts, while your read models are optimized for blazing fast reads. Let's address a very common challenge: handling unique constraints, such as ensuring unique email addresses during user registration.
Right. How do you do that if everything's eventually consistent?
Great question. In an eventually consistent system, how do you guarantee uniqueness before an event is fully processed and projected across all components? You can't put a unique index directly on your event store's messages table, because that table is designed for pure append-only writes, not for querying current state.
Okay, so no unique index on the messages table. Then what?
The clever solution on the right side is to implement a unique index on an inline projection.
An inline projection. What's that?
It means that as events are captured, a quick synchronous process, often within the same database transaction as writing the event updates, a small specialized table that does have a unique index on the email address.
Ah, a separate lookup table updated transactionally.
Exactly. This user email's lookup table, for instance, would ensure integrity without burdening the primary event store. It's purpose-built just for that uniqueness check. Now, you might be thinking about the trade-off here: eventual consistency.
Yeah, there's still a gap, right?
There's a very small window, typically on the order of milliseconds, where two truly concurrent register user commands with the exact same email address might both be initially accepted by the application layer before this inline projection enforces uniqueness.
Okay, a tiny race condition window.
It is. And this raises important questions that you must discuss with your business stakeholders. How likely is this specific race condition to occur in our system? How bad is it if it actually happens? Is a soft failure, like a notification to the user that their email is already in use, acceptable? Or do we need hard, immediate consistency?
Whose constraint is it, really?
Exactly. Often, after careful consideration, we decide that unique email addresses are not a fundamental, immutable property of the identity itself in the same way an event ID is, but rather a validation specific to the registration process. For these scenarios, we can often live with eventual consistency for such a small window and handle the rare conflict gracefully after the fact, perhaps by notifying the second user that the email is already taken. This conscious decision about acceptable trade-offs is absolutely crucial in distributed systems.
Right. Understand the trade-off and design for it.
Another critical aspect of CQRS in practice is managing race conditions on the right side through optimistic concurrency control.
Okay, this sounds important.
It is. This deals with the problem where multiple instances of your component, or even multiple threads within a single instance, try to write new events to the same event stream concurrently.
Two updates hitting the same user stream at once.
Exactly. How do you prevent data corruption when this happens, ensuring that the latest write is based on the true latest state and not on a stale view? The solution lies in that expected version parameter in our write message function that we discussed earlier.
We're back to that.
We are. When a component decides to write a new event, it includes the expected version of the stream, the version it believes the stream is currently at based on when it last read it. The write message function in PostgreSQL then checks the actual current version of that stream in the database.
Before it writes.
Before it commits the write, yes. If the stream's actual version has changed since that component made its decision, meaning another write occurred in the interim, and the stream is now at a higher version than expected, the write operation fails.
It rejects the write.
Yes, typically with a concurrency exception. This prevents a corrupted or inconsistent state from being written. This mechanism is vital for maintaining transactional integrity and preventing career-limiting situations.
Chuckles. Yeah, you want those.
Like two simultaneous $5 deposits somehow leading to only a single $5 credit on a bank account because the second deposit overwrote the first, rather than adding to it. Optimistic locking prevents that.
Crucial for financial systems, or really anywhere state integrity matters.
Absolutely. Finally, let's talk about managing interdependencies and partitioning for scale. Autonomous components, especially the ones that manage aggregates and their event streams, are inherently stateful.
Stateful. How so?
Well, they often load aggregate state into memory to make decisions. This makes horizontal scaling tricky. If you simply run multiple instances of the same component without coordination, you risk having each instance trying to process the same work.
Like handling events for the same user ID stream.
Exactly. Which leads to race conditions or duplicate effort within the read model processing, or even conflicting writes if you didn't have optimistic concurrency.
So how do you scale out stateful components safely?
The solution is to intelligently divvy up streams among instances based on partitioning.
Partitioning the work based on the stream.
Precisely. A practical example of this involves assigning each component instance a number, say from 0 to n1 for n instances. When a new message arrives for processing, you compute a numeric hash of the stream name associated with that message, e.g. the hash of user123.
Okay, hash the stream ID.
Then you take the modulo of that hash by the total number of instances, n. If the result matches the instance's assigned number, that specific instance processes the message.
And if it doesn't match?
It skips it, knowing another instance is responsible for that stream.
Clever. So each instance handles a subset of streams.
Exactly. This approach allows multiple instances of the same component to work on different streams concurrently, greatly improving scalability and throughput without introducing conflicts or requiring complex distributed locks. Each instance handles its dedicated slice of the event streams, ensuring that each stream is processed by only one component instance at any given time, preventing internal race conditions within the component's read model updates.
Software isn't static, and that's especially true for successful systems. Business processes change, our understanding of data evolves, and so does our code. One of the biggest questions then becomes, how do you handle changes to event schemas when your event store is, by its very nature, immutable? You can't just go and alter a past fact, can you?
That's absolutely right, and it's a critical consideration for any long-lived event-sourced system. You can't change history. In practice, it's unavoidable in a living system not to have event schema migrations. These changes can arise from various sources. A simple bug, like a typo in a property name or missing piece of data.
Happens all the time.
New business requirements that dictate you store additional information, like adding a full name field to a user-registered event, or even internal refactorings where you rename event classes or move them to different namespaces in your codebase.
So how do you cope if you can't change the stored events?
We have several strategies for managing these evolutions gracefully. The most straightforward and often the first line of defense is backward compatibility. This means you design your system to support both the old and new schemas simultaneously for a graceful transition period.
So your code understands both versions?
Yes. During the transition, your code needs to be able to read and interpret both versions of an event seamlessly. Another highly useful technique, especially for developers, is event type name mapping. Many frameworks, and even a vanilla approach where you control the Postgres interactions, will allow you to map your code's internal type names, what developers often call class names or types in their programming languages, like ecommerce.orders.order status changed in C#, or order status changed in Java.
The code name.
To a consistent snake-cased event type name, like order status change, that's actually stored in your database.
Ah, Separate the stored name from the code name.
Exactly. This crucial separation allows you to refactor your code's type names and namespaces without ever altering the immutable event name that's permanently stored in your database, giving you significant refactoring freedom.
Okay, that helps with renaming classes. What about properties inside the event?
For renamed properties within an event payload, you can leverage serializer attributes in your programming language. For example, if you're using JSON serialization, you can often add an attribute that tells the deserializer, hey, if you see an old property name like first name, just map it to my new given name property in the code.
So the code handles the mapping during load.
Exactly. This works brilliantly for code. However, a word of caution here.
Uh-oh.
If you're querying your raw event data directly in your database using SQL, say for debugging or some ad hoc report, that query will likely fail if you're trying to use the new property name to find data that was stored with the old name. Your database doesn't understand your code's serialization hints.
Right, the database only sees the raw JSON. Good point.
The most involved strategy is upcasting. This involves writing specific code that transforms an older event schema to a newer one during deserialization.
Transforming on the fly as you read.
Correct. So every single time an old event is read from the store, your upcasting logic runs to make it look like the current new version. This is powerful for handling complex schema evolutions. However, a major warning here, and I can't stress this enough.
Okay, another warning.
Upcasting code runs every single time that old event is pulled from the store and deserialized. Every single time. If you put anything heavy or slow in there, especially external calls like network requests or I/O operations like hitting another database or an API,
Oh no.
you will immediately introduce massive performance issues, hitting the dreaded N+1 problem where one read of a stream turns into a cascade of slow external requests. Also, be extremely mindful of synchronous versus asynchronous calls. If you define an async upcaster, it will throw an exception if your code later tries to read events with synchronous calls.
So keep upcasters fast and simple, pure transformations.
Keep them pure, fast, and in-memory transformations. Absolutely.
That's a vital warning for managing evolution. It's also important to think about the data lifecycle and archiving. Not all data needs to be hot and instantly accessible forever, does it?
Exactly. No, it really doesn't. This is a crucial aspect of long-term data management in these systems. We can categorize data by its usage. Hot data is frequently accessed, usually daily, for active transactions and operational processes within your right model. Think of the current state of a user's shopping cart.
Active, recent data.
Warm data is used sporadically, often read-only, for things like UI displays, historical searches, or reporting in your read models. Perhaps a user's past orders from 2 months ago.
Less frequent access.
And cold data is rarely, if ever, used in the application itself, or only for very long-term analytics, auditing, or fulfilling legal obligations. Think of orders from 5 years ago.
Archival data.
Right. Once you realize this distinction, you can separate storage for each type, optimizing for cost and access patterns. For instance, you might keep active event streams in your primary PostgreSQL database relatively short-lived, while archiving inactive streams and their events to cheaper, slower storage.
Like S3 or Glacier.
Potentially, yeah, retaining only necessary read model documents for occasional historical queries. Techniques like event archiving and stream compacting can significantly reduce the size of your active dataset, which in turn can reduce the need to maintain every single historical event schema in your hot path, simplifying your evolution strategy over time.
Let's fast forward a bit. You've shipped your amazing event source system, it's live and it's doing great things, but inevitably something's amiss. Maybe users aren't getting their registration emails or a video isn't transcoding properly. How does this unique architecture actually help you debug rather than hinder you with its distributed nature?
This is one of the profound, often unexpected benefits of event-sourced systems. It can actually make debugging easier in many ways. Remember those traceids we've been so careful to include in the metadata of every message?
Yeah, you mentioned those a few times.
This is precisely where they shine and become your best friend. All messages resulting from the same initial user input or originating from the same logical flow, whether that's a user registering or a video being uploaded, will carry the same traceit.
So you can follow a single request across the whole system.
Exactly. This allows you to easily track everything that happened in response to a particular user request across all components, even spanning your entire distributed system. You can literally trace the complete journey of a single user action and all its cascading effects, seeing exactly which events were produced and which commands were processed in what order by which component.
That sounds incredibly useful, like a distributed stack trace.
It's like having a perfectly synchronized multi-camera replay of your entire system's activity for that one request. Beyond tracing, you can build incredibly powerful admin portals or debugging views right on top of your event data. For instance, you could have an administrators table. This isn't your primary user aggregate, but rather a simple aggregated view specifically for debugging user activity.
A read model just for admins.
Pretty much. This table would consume events like user registered, registration email sent, and user logged in to track a user's current registration status, whether their email was sent, and their login counts. This gives you a high-level, human-readable overview of what happened for any given user. You can also create an admin streams table. This aggregates information about all the event streams in your message store.
A meta view of the streams themselves.
Exactly, showing you the stream name, the message count for each stream, and the last message global position. This offers a quick, system-wide overview of activity, letting you spot stuck streams, streams with unexpectedly high activity, or even identify components that aren't processing events as quickly as they should, all at a glance. It's like a dashboard for your events.
That sounds very powerful for operational monitoring, too.
Absolutely. And critically, because events are the immutable source of truth, you gain unparalleled replayability for investigation. If you discover a bug, you can effectively rewind to any point in time by examining the specific event stream. You can reanalyze a sequence of events to understand exactly a bug's origin or how a specific problematic state was reached.
Replay the crime scene.
Exactly. It's like having a perfect, unalterable flight recorder for your entire application, allowing you to recreate and understand any scenario with absolute fidelity. You don't need to guess. You have the facts.
Testing is absolutely critical for any successful software project, even more so when you're dealing with distributed systems. So how does this event-driven autonomous architecture change how you test your code? Does it add complexity, or, surprisingly, does it make testing profoundly simpler?
It makes it profoundly simpler and significantly more reliable, in my opinion.
Simpler? How so?
Here's why. There's no disparity between how your autonomous component runs in a production environment and how it runs in a test harness. Think about it. Your component's job is to receive messages, commands, or events, process them, and potentially produce new messages or update a read model.
Okay.
It has absolutely no idea if a message is coming from a live production system, from a replay of historical events, or if it's coming from a controlled test environment. It operates in the exact same manner.
So the component doesn't care about the environment.
Not at all. This eliminates a huge class of testing problems often faced in traditional architectures, where your test environment never quite mirrors production, leading to works on my machine syndrome.
All right. The dreaded environment drift.
This leads to incredibly focused tests. You test components by providing them with specific messages, whether they are commands that trigger new events or events that drive updates to read models and then asserting their output. The output will typically be new events written to the message store or specific changes to a read model.
So you test input messages and output messages or state changes.
Exactly. For instance, to test the homepage aggregator we discussed, you'd send a video viewed event directly to its event handler within your test suite. You might send it once, then send it a second time. Then you'd query the pages table in your test database.
The test read model.
Yes. To assert that the video's watched count is correct, and crucially, that it has been updated idempotently, meaning processing the second video viewed event didn't double count the view.
Testing idempotence directly.
Absolutely. Speaking of which, idempotence testing is not just important, it's explicitly required. If idempotence is fundamental enough to warrant the emphasis we've used throughout this deep dive, then it's absolutely important enough to explicitly test it.
Test it every time.
Always, always test your message handlers for idempotence by calling them multiple times with the exact same message and asserting that the system state changes only once or in the precise intended idempotent way. This builds tremendous confidence that your system will behave correctly even under high-load, network retries, or component restarts.
That's fascinating. And what about those notoriously complex integration tests? In traditional distributed systems, setting up and maintaining them can be a huge headache.
Right, the brittle end-to-end tests. This architecture even changes how you approach integration testing, often for the better. Since you have a complete immutable log of all state transitions stored in your message store, you can leverage production monitoring as a form of testing.
Testing in production, isn't that risky?
Not necessarily testing on production in the traditional sense, but observing production. You can set up automated observers or reporting tools that sample message workflows in production and then verify their correctness after the fact.
Passive verification.
Exactly. This is often far easier and more reliable to set up than trying to replicate your entire complex distributed system for brittle, slow, end-to-end integration tests that might never truly capture the nuances of production traffic. You could, for example, have an observer that continuously scans for user-registered commands and then checks if a registration email sent event followed within an acceptable time window.
And alert if it didn't happen.
Precisely. If not, it can immediately alert you. This kind of real-time post-hoc verification provides incredibly high confidence without the overhead of massive, complex test environments.
Wow, what a deep dive today. You've learned how to fundamentally shift your approach to software design, moving from a mutable, often tangled, state-based model to one that captures every single change as an immutable event. You've seen how to build systems that communicate explicitly through powerful message contracts and can scale effectively, all powered by the robust, familiar capabilities of vanilla PostgreSQL.
You now understand that the true monolith isn't about deployment. It's about a canonical, tightly coupled data model that stifles evolution. By embracing event sourcing and explicit message contracts, you gain tremendous flexibility, profound auditability, and the ability to build true autonomy between your components.
Yeah, that autonomy is key.
Absolutely. You now have the fundamental knowledge to leverage powerful concepts like optimistic concurrency control, idempotent processing, and intelligent stream partitioning to build truly robust, scalable, and maintainable systems designed to last not just months, but for decades.
So now that you understand that software is easy to write but hard to change, what single piece of your current system would you start to model as events today to make it easier to change tomorrow? It's a powerful thought to chew on. What's that first step you could take?
And the journey of mastering event sourcing is continuous. There's always more to explore. Consider diving deeper into topics like managing even more complex concurrency patterns with advanced stream partitioning strategies, or exploring how snapshots can further optimize your read models for extremely high-volume scenarios. The principles we've discussed today are a fantastic foundation, though.
We truly hope this deep dive has sparked your curiosity and provided you with actionable insights that you can take directly into your own work. Thank you for joining us on this exploration. We invite you to continue your learning journey and apply these powerful ideas in your own projects. Until next time, keep digging into the details.